Hello everybody. This is the first session of our statistical modeling course. In this session, I'm going to explain some very basic materials about probability distributions. I'll start with a very simple data set from a single group and just one condition. For example, the group can be a population of adults, and the feature we aim to study can be their weights. Now assume we have some data points, for example these red crosses here, and we want to study them. One of the most simple things that we can study about this data set is the number of observations for each data point, or in other words, their frequency. We can visualize it using a histogram. To plot a histogram, we should discretize our dataset into some bins and simply count the data points in each bin. For example, in this bin we had 4 data points, and in this bin we had 19 data points. We can calculate some descriptive parameters in order to explain these data better. First descriptive number is the mean. Mean is simply computed as the sum of all data points divided by the number of them. Mean tells us about the central tendency of the data. In this example, the mean is close to 0. The next descriptive number is the standard deviation. Here I showed mean plus standard deviation minus standard deviation. A standard deviation can explain the spread, the diversity of our data. As you can see here, this data set is somehow symmetric. It looks somehow symmetric around the mean. Now, let's look at another data set which doesn't look symmetric like the other one that we saw in the previous slide. Again, red crosses represent our data points, and we have plotted the histogram here and also computed mean and standard deviation and showed here. We can see that in this case, neither mean nor standard deviation can describe our data set well. So, what we can do? Actually, there are other statistics that we can calculate for these data. These statistics that we are going to talk about them right now are called non-parametric statistics. Non-parametric statistics are the statistics that have no assumption about the form of the data. Mean and standard deviation were parametric statistics. They had assumptions about the form of the data and are reasonable only when those assumptions come true. A non-parametric statistic for the central tendency is the median. The median is the value that half of our data points are smaller than that value and half of our data set are larger than that value. I have shown the median for this data set here. You can see the median can very well explain the tendency of our data set. A non-parametric statistic to explain the spread of our dataset is an interquartile range. I have shown 25th and 75th percentiles here. 25th percentile here is the value that 25% of our data is below that, and 75% of our data is above that. Also, 75 percentile is defined in a similar way. According to this definition, median is the 50th percentile. Okay, now we can see that non-parametric statistics for this data set seem more reasonable than parametric statistics. Here we can see again the formulas for mean and standard deviation. We can simply calculate mean and standard deviations using these formulas. I have to mention here that for non-parametric statistics like median, there isn't any explicit formula like mean and standard deviation. Now let's take a closer look to one of the most famous probability distributions, the Gaussian distribution. In this figure, the x-axis represents the quantity that we are studying, and the y-axis shows the likelihood or the probability of x. This red curve shows the Gaussian distributions, and in this case the mean equals to 0 and the standard deviation equals to 1. Here is the formula for Gaussian distribution. In this formula, first we subtract all the data points from the mean. This is the term that shows the subtractions of the mean and every single data point. This way we can obtain somehow the deviation from the mean. Then we normalize these deviations by dividing these values by sigma. We score this term because both positive and negative deviations have the same effect on our distribution. Then what does this exponential term do? This term gives us this bell-shaped curve. Finally, we have this normalization term, this normalization constant that scales the height of this distribution such that the area underneath this curve equals to 1, as any other distribution should have this condition. Okay, next we are going to talk about the error bars. But before that, we have to review some basics of the process of sampling. Here at the left, we can see a population. Population is a term that refers to the space of possible measurements we can perform on the results of a specific experiment. In this example, our population can be explained with a normal distribution, as we can see here, normal or a Gaussian distribution. Now assume that we draw 10 samples from this population and calculate their mean and show the resultant value here. So this cross is the mean of these 10 samples. If we repeat this process of sampling and calculating mean for many times, we can obtain a distribution like this one here. And next, I'm going to talk about this distribution a little more. As we can see, this distribution is also Gaussian, but the standard deviation of this distribution is smaller than the standard deviation of the first population. But the thing that I want to mention here is that the mean of this distribution is identical to the mean of the population, the first population here. So the mean here is identical to this mean. Now, suppose that we want to do the same analysis for a non-normal distribution. We don't use parametric statistics in non-normal cases. Instead, we use bootstrapping. So, what is bootstrapping? Bootstrapping is a non-parametric procedure that can be used to quantify the uncertainty of the statistics that we have computed for an arbitrary distribution, not necessarily normal distribution. The first step is to draw samples from this data that is not normal, exactly the same size of the data. Therefore, it's obvious that the sampling is with replacement and some data points are repeated in the sample dataset. For example, if the data has 20 data points, each sample data must also contain 20 data points. Some of them are repeated, and some of the data points are not here, and some of the others are repeated several times. We show the median of each sample data set here in the right figure. After repeating this process several times, we can plot the histogram of the medians, and we can also calculate the median of this data set, actually the median of medians, and the percentiles, 25th percentile and 75th percentile. Actually, instead of 25th percentile and 75th percentile, here I showed the standard errors. Actually, standard errors show the interval that 68% of our data points lay in it. So 68% of our data points are in this interval. Now, for presenting the results, we have several options. We can simply show data points just like spikes, as I showed here, or we can plot their histogram, or another option is to use a kernel, a very smooth kernel for each of these data points, and just average them to have something like this. Therefore, these small curves here that are not just as old as these large ones show the kernels that we fit on each data point, and this large one that we can see here is the average of them. The last issue I want to discuss in this session is the bin size. We can choose different bin sizes. If we choose a bin size too small, histogram is somehow unstable. Therefore, if we sample a new set of our data, it's highly probable that we obtain a different histogram from the histogram shown here. If we choose the bins too big, bins can't reflect the features of our data very well. For example, in this case, we can see that there should be a bump somewhere here, but in this histogram we can't see a bump here. We just have one bump, one large bump here, and this month is covered. So we have to choose a bin size in between these two values, not too small, not too big, so that we can reflect all the features of our data, almost all the features, not actually all of them. I think somehow it's impossible to show all the features. We aim to show as much as features as we can, and on the other hand, we want to have a histogram that is stable and doesn't change too much when we change the data sample that we are showing. Okay, that's it. It was the first session of our statistical modeling course. I hope you have enjoyed it, and